Alright, now why I'm taking my time to throw light on this orbital configuration or hybridization is because it's one of the key areas that question comes out from in JAM. We have lots of question evolving from this aspect of chemistry. Now, the shape of an sp3 carbon. Don't forget sp3. The S there is talking of the 2s1, and the p3 is talking of 2p1 in the x direction, 2p1 in the y direction, 2p1 in the z direction. So in order to get as far away from each other as possible, thus minimizing electron to electron repulsions, the sp3 orbitals are arranged in the shape of a tetrahedron. So if you arrange it like, for example, say in a parallel direction, or parallel to each other, we're going to be having electron repulsion, because like charges will repel. Don't forget, I know that electrons are negative, they're negatively charged. So bringing two negatively charged particles together becomes a problem. So in order to avoid that, they are now arranged in a tetrahedron, or you say tetrahedral pattern. For example, CH3. That's the tetrahedral pattern. Now, we have with bond angles of 109.5 degrees. Please take note. This is another key question that comes out in JAM examinations. What is the bond angle in the can ask you now, for example, in CH3? Or what is the bond angle in an sp3 carbon? The answer is 109.5 degrees. Now you can see the arrangement below. So this is how they are arranged in such a way that the electron to electron repulsions are going to be minimized. Now look at the shape of an sp3 carbon. So you have one S, then you have the three P's. One S is now bonded to the three P's carbon. Now when we react that with 4 hydrogen 1s atomic orbitals, see what you're going to have: bonding, covalent bonding. So one of the electron in the hydrogen element will bond with each of the p3 orbitals. And then you have methane, CH4. So you can see 4 carbon sp3 hybrid orbitals reacting with 4 atoms of hydrogen. 4 atoms of hydrogen, you have CH4, which is methane, or also called natural gas. Now, bonding in ethane. Let's look at the bonding in ethane. I'm taking my time to give the analysis of all this because it's the foundational to really understanding organic reactions. Once you have a good understanding of bond reactions with carbon and other elements, it becomes easy for you to adapt to or understand organic reactions. Now, bonding in ethane, what do we have? We said bonds arise from the overlapping of orbitals on adjacent atoms. Overlapping of orbitals give rise to bonding. Bonding arises as a result of overlapping of orbitals. End-to-end overlap of sp3 orbitals produce a sigma bond. So if it's an end-to-end overlapping, the end of one orbital overlapping with the end of another orbital, a sigma bond is produced. And this is experienced in all single bonds. All single bonds are sigma bonds. An example of compounds that have single bonds are the alkanes. Alkanes are a classical example of compounds with single bonds. Alkanes. Alkenes have double bonds, and therefore they are unsaturated. Alkynes have triple bonds, and they are also unsaturated. So alkanes, the bonds that exist in alkanes are sigma. They are all sigma bonds. Also, free rotation is possible around sigma bonds. Free rotation. That is why you can see, because of the presence of the single bonds. For example, let's take a classical example of methane, CH4. Can be written as H4C. But why? Because of sigma bonds present there. So sigma bonds give rise to free rotation around the compounds. It gives rise to free rotation around the compound. Are we there? Also, we said each carbon in the ethane molecule, for example, look at C2H6, which is CH3. We're going to look at all that, naming of compounds and all that. We're going to see all that in upcoming classes. So each carbon in the ethane molecule is sp3 hybridized and tetrahedral in shape. So tetrahedral structures have sp3 hybridization. And the bond angle, don't forget, I said the bond angle between them is 109 degree. Now, free rotation is possible around the carbon-to-carbon bond. I told us that before, by virtue of the sigma bonds present. So we can see below, we can see the bonding in ethane, CH3, can be written as H3C. Alright, can you see? So we can see the carbon in the middle carrying the sp3 carbon atom in the middle, bonding with 3 hydrogen on the right and 3 hydrogen atoms on the left, and we can see the structure below. We can see the structure below. All right. So on bonding, before we'll conclude on bonding, we'll see that carbon chains. All right. So we said each carbon atom can form 4 bonds. Each carbon atom can form 4 bonds, either to other carbon atoms or to different atoms such as hydrogen, oxygen, nitrogen, sulfur, phosphorus, and the likes. Now we'll see that. Let's look closely at this bond. We'll see that. Look at carbon to carbon bond. We want to see now how is this bond possible. Now let me show you quickly. Carbon is what? 2,4. The traditional configuration 2,4. Now when it bonds with another carbon having 2,4, what do you see? You see that you have double lone pair. You see lone pair electrons. You see 2 pairs in the middle. What do I mean? 2,4. Okay, then 2,4. So when they bond, you'll be having one carbon having 2 electrons inside. The other one also 2 electrons inside. Then outermost shell, you have 4 from the first one, 4 from the second one, making a total of 8 connecting both of them. So you have 8 electrons outside. 8 electrons outside. 8 electrons outside. So you have 2, then you have 1, 2, 3, 4. In between them, the rest shell, you have 4. All right, this is what I mean. You have carbon 2, 4, 2, 4. Okay, when you bond them, see what he said. He said 3 more sides to make bond. So in between them, you see that 4, 4. 2, 2 will be used. Remaining 2 on the outermost shell. That's why they said 3 more sides to make bonds. Okay, so when you carry out the covalent bond, carbon to carbon, you see what I mean. Now this one is carbon to carbon to carbon to carbon bond. 4 bonds. Right, you see that. For example, let's take the case of methane now, CH4. Now let's, like I said earlier on, C, you have 2, 4. Can you see 4? 4 outside and 4 hydrogen atoms. So those 4 hydrogen atoms will bond with each of the electron in the outermost shell of the carbon. It now becomes 2, 8, so that it can get to octet structure. That was the simple explanation I was trying to give. The same thing happens to the carbon to carbon bond. So I said earlier on, each carbon atom can form 4 bonds, because it has free 4 valence electrons in its outermost shell. Now multiple bonds. Carbon atoms form 4 bonds to other things, but sometimes those bonds are multiple bonds, or multiple bonds are either double bonds or triple bonds. So you can see the single bond, carbon to carbon to carbon to carbon, the single bonds, and we can see the double bonds. The double bonds, you have 4, 4, which is 8, that's double bonds. You can see the double bonds resulting from the sharing of what? 4 electrons. So like I said earlier, carbon to carbon bond, you have 2, 4, 2, 4. When they bond, you now have 2 on this side, 2 on this side, inside the innermost shell. Then the outermost shell, you have 4 on this side, 4 on this side. When those 4, 4 combine, you have 8. That's why they said double bond results from the sharing of 4 electrons. while triple bonds resulting from the sharing of 6 electrons. Carbon to carbon bond, 6 electrons are shared. So when 6 electrons are shared, for example, you have 2 4 on this carbon atom, 2 4 on this carbon atom. Now the 4 outside. If I bring out 3 from the 4 on this side, I bring out 3 of the outermost electrons on this side. I will have 6, remaining 1 free one on the first atom and 1 free valence electron on the second atom. And that's why if you are writing it, alkyne compounds, you see that the last electron can only bond with 1 hydrogen. If it's alkene, the last two free valence electrons can bond with 2 hydrogen, while alkane, the 3 valence electrons can bond with 3 hydrogens. So the number of valence electrons will determine the number of bonds, the number of hydrogen that will be required. For alkanes, you have 3 valence electrons on the outermost shell of the carbon, which makes it to react with 3 hydrogen atoms, so that you can have CH4. For alkenes, you have 2, which makes it react with 2 hydrogen atoms. That is why you see ethane, you have methane, you have CH4. Look at ethene, you have C2H4. The bond connected to the carbon connected to the double bond can only take 2 hydrogen. Therefore, alkyne, the same thing. The carbon connected to the triple bond can only take 1 hydrogen. So this is just the summary of hybridization and bond formation in carbon.